Hi everyone, in this video we're going to go through part 2 of Lab 2 where we take our data that we've collected on the Sternberg task and we now build the Sternberg plot. So what exactly am I talking about? Well, if we take a look at the data itself, you can see here's an example of what the data would look like in GitHub. On your assignment sheet there is a link that will take you directly here. To the relevant address. So if you're watching this in a different semester, it might be a slightly different semester than fall 2018 when this video is recorded. But nonetheless, we've got this raw data. And what we want to do with that raw data is do something like this. So let's take a look at Sternberg 1966. This is the actual paper as it was published in the journal Science. And the paper was high-speed scanning in human memory. And we did essentially a fairly close replication of Sternberg's experiment. But this figure right here, figure 1, that's the one that we want to draw. So essentially we need to take all that raw data and we need to convert it into a scatter plot that has some error bars and a regression line. And we'll also learn how to compute the slopes and intercept of this regression line. So that's what's in store for this video. So how exactly do we get started on this? Well, let's go look in RStudio and see what we need to do. So of course, anytime you want to build a plot or do anything with some data like this is we need to read in the raw data files. To do that, we're going to use some functions from the tidyverse library. So of course, the first thing that we usually do in this course is we load our tidyverse library. And so we'll just do Control Enter on that command. Now, we want to read in our raw data files. So I'll make a little comment here, read in raw data files. First thing that we do, this is very similar to what we've done in the previous lab this semester. We're going to take raw data and we're going to assign that to an empty data frame. So we do something like this. Okay. Now I'm going to go over here, click on environment, clear all this stuff out. There we go. So right now all I have in is an empty data frame. Now we need a file stem. Now the file stem is what's different every semester that we do this. But essentially what it is remember the process is we loop over our subject numbers. And if we take a look at the data, you can see that in this data set it goes up to subject 27. So we want to loop that index from 1 up to 27. But any one individual data file is going to have basically the same full file name, except it just will say 1 or 2 or 3 up to 27. So the question is, how do we find that file stem? So if we just click on any one of these, I'm going to click on subject 1. It'll take a minute because this is a pretty big data set. Let's let that load up. You can see we've got a whole bunch of data that we typically get from Open Sesame. Now that went back, sorry. Let's go back here. Okay, so there's subject 1 again. What I want is I want the raw version of this data file. And this is going to look really ugly, but it's going to give us the correct address, the correct web address to pull the data from. So I'm going to click on raw. Now pay no attention to how ugly that is. What I really want is everything before the number 1 in the subject name. So I'm just going to highlight all that stuff, that raw.github user contents, etc. I'm just going to copy that and then go back over to RStudio, and I'm going to call my file stem that. So I'm going to paste in that big long thing that I just copied. Okay. Now you probably have a version of this from Lab 1, and the short answer is it'll just change to Lab 2. Everything else will be the same. But the way to get that file stem is exactly as we just went through. Okay, so let's execute that, and that gives us the file stem. Now we can do our loop. So I'm going to say for n 1 up to. Now, I don't want to do everything that you're going to have to do in your assignment, so I'm not going to pull in the full data set. I'm just going to go maybe with the first 25, let's say 25 data set. I'm thinking about this as I'm working. Is this what I want to do? And I think it is. So we'll play like there's only 25. Now, depending on the semester that you're watching this video in, there will be more or less subjects in your actual data set. So I'm going to say for n is 1 up to 25, and I'm going to do the following. First of all, I'm going to define a file name based on that file stem. Basically what I want to do is I want to take that file stem and I want to paste the actual number onto it and then put a .csv at the end. So the way I do that is I say paste file stem comma, n, so that's going to stick the n that the index is running from 1 up to 25 on. And then I want to put a .csv at the end, so I'll put that in quotes. And then I want to be sure and say that my separator has no space. So I just put in a double quote and a double quote with no space in between them for my separator. Okay, so that defines the file name. Then I'm going to actually pull in the file. I'm going to say temp equals read.csv, and then I'm just going to say use that file. So that's going to read that file name in and call it temp. Now from that temp, I'm going to select only a few of those many, many columns that it has. So I'm going to say d equals select. Now the way select works is I say from temp, I select the following variables: block, correct, present, set size, and the S is capitalized, the middle S is capitalized, and then response underscore time. So those are the variables that I want to pull in. Now, one little cleanup thing that I have to do here is, since every student in the class pulls in 3 data sets, the subject numbers on all those data files are either 1, 2, or 3, but I want them to actually match whatever this index is. So I'm going to say $subject nr, so I'm going to assign the subject number for each data frame to be n. So if it's subject 1, then the subject number is going to be 1. If it's subject 2, the subject number is going to be 2, etc. Now I've pulled in that D. I'm now going to add that to that data frame that's called raw data by saying raw data equals rbind, which is just bind the rows together from raw data with the additional data frame D. And then that should do it. So all we've got to do is execute this loop. So I'm going to take my cursor up to the beginning of the loop and then hit Control Enter. It'll take a minute because it's looping through some number of data files. But that will do it here in a second. We should see it show up in the environment. Okay, and of course, the more data you have, the longer it takes. For some reason, this is taking a while. There we go. Okay, so raw data looks like we have 3,450 observations. Let's do a check. Remember, it was 126 trials plus 12 practice trials. So I think it's 138 trials per person, and if that's times 25, that gives us 3,450, which is exactly the dimension of raw data. So this all looks good. Okay, so that's the raw data frame. We can click on that, kind of see what it looks like. So here we got our subject numbers, we've got all kinds of stuff here, and this is just going to go on forever. So we got all the stuff we need. So what do we do with this? Well, the first thing we want to do is we want to get rid of these practice trials. So I'm going to say get rid of practice trials. Because remember, if you look in the raw data file, the block is 12 practice trials followed by 126 experimental trials. We only want the experimental trials. So what we're going to say is we're going to filter out those practice trials. So we're going to call this data. Okay? Instead of raw data, we're going to call it just data. And we're going to get it by saying raw data, and then we're going to pipe that into the filter command. And what is the filter? Well, the filter is block is not equal, so that's exclamation point equal, to quote practice. So anytime the block is equal to practice, we want to throw that out. And I'm going to do one more thing. Remember, I like to make things easy. Open Sesame calls response time response underscore time, and I would much rather it just be called RT. So I'm going to say mutate RT equals response time. And so that's just going to give me a new column called RT that I can work with now instead of this big long name. This is totally optional, but I think it makes things easier. So I'm going to go up into the beginning of this big block, this code block, and I'm going to hit Control Enter. Now I've got a data file that is smaller than my raw data file. So that tells you how many practice trials I have removed, just whatever the difference between 3,450 and 3,150 is. And of course, with whatever your data set is, you'll need to do the arithmetic accordingly. Okay, that's getting rid of the practice trials. Now we only want to do response times on the correct trial. So we're going to get rid of the errors. So let's get rid of errors. And we'll do something pretty similar here. There's too many R's there. There we go. All right, so get rid of errors. What do we do? Well, let's call this clean, because once you've gotten rid of the errors, that's a good name for it, right? Again, you can call these whatever you want, but this is what I like. Clean, I'm going to start with data, and I'm going to pipe that into another filter command. But this time, I'm going to filter on correct. and I want the correct variable to equal 1. So basically, anytime it's equal to 1, that's what I'm going to keep. And so I'll hit Control-Enter in this block. And now I'm down to 2,811 trials. So if I start with that 3,150 that were experimental trials, and I subtract out the 2,811, then that tells me that across this task, across these 25 participants, I made 339 errors. Okay, so again, this kind of filtering these things sequentially like this lets you easily count the number of practice trials, the number of errors, etc. Now we're pretty much where we should be, right? But before you start doing any sort of analysis, you should really take a look at your RTs. That's what we're interested in here. So let's do a quick visualization of the RTs. And the way I like to do this is using a ggplot. So I'm going to take clean, and I'm going to pipe it into a ggplot command. Now ggplot, you have to define an aesthetic. This is just kind of defining how it looks. And really what we want is we want the x-axis to be the RTs. We're going to look at the distribution, right? So we'll just say x equals RT, and then we'll add an element that's just a density function. So we'll take a geom density and add that to it. So if we hit Control-Enter here, we should get a little density plot. And there it is, and you can already see that we've got a problem. The problem is that this density plot is indicating that there are several trials out here for which the response time is out here at 7,500, 10,000. But remember, in the coding of the experiment in the previous video, we wanted to cut off each trial at 2,000 milliseconds. So what this means is that some of the students didn't put that 2,000 millisecond requirement on the response collectors, right? And so we've got to get rid of those trials that are bigger than 2,000 because those shouldn't have been there. So here's what we're going to do. We're just going to do this instead. So this is going to help us get rid of those extra RT trials. Let me move this up the screen just a little bit. So here's what we're going to do. We're going to say that we're going to redefine the set clean. And we're going to take it by starting with the data, right? This is just the stuff that has only the experimental trials. And we're going to filter. First of all, we want only the correct trials. And we want RT to be less than 2,000. So essentially, we're redefining this clean data set to not only filter out the errors, but also filter out the long RTs. All right, so this will keep only the RTs that are less than 2,000. So if we do that, now you can see we're down to 2796, and before we were at 2811. So that tells you there were, looks like 15 of those extra trials that that we needed to throw out. Okay. All right, so that's good for now. Now we've got the data set that we can work with. So at this point, it's probably good to talk about our overall design. And to do that, I'd like to look back at the Sternberg plot. So if you look at this plot, you can see how we're going to do this plot. So there are dots for each of these numbers 1 through 6, which represent the length of that memory set, as Sternberg calls it, the number of symbols in memory. So we're going to have 6 lengths possible. We'll have dots for probe not present and dots for probe present, okay? And then we'll also have all of our subjects as well. So essentially, let me go over here to write this down a little bit. Let me clear this out. Essentially what we have is this. We have 25 subjects, and we have, let's see, what else? We have 6 positions, 6 lengths, 1, 2, 3, 4, 5, 6, times 2 probe conditions. So this is a 25 by 6 by 2 design. It gives us 300 total conditions, 300 total means that we need to collect. So essentially what we need to do is we need to collapse this big data set that looks like 2,796 trials down into 300 cells. Each of the cells is defined by subject, set size, and probe condition. So the way to do this, of course, is just to do one of these tidyverse things where it's group by and summarize. So here's how we do it. We're going to do a little collapse into design cells. Again, this is no different than what we did with the flanker task in the first lab. We're going to name this data set collapsed, and we're going to get it by taking clean and piping it into a group by and summarize command. So we'll take group by, and what are we going to group by? We're going to group by those three variables, right? So subject, which is subject NR, subject underscore NR. Present, which codes whether the, let me go in the same order that's up here. So what do we got? 25 by 6 by 2. So we got 25 subjects, we got 6 set sizes, and then the last one is present. And remember, present is either probe is present at the probe trial or the probe is absent. So we're going to group by, and then we do a summarize command. And what we're going to summarize is the mean RT, I'm just going to say MRT for that, is the mean of RT. Okay? So let's do this and see what it looks like. Okay. Now, if you look at collapse, look, it is 300 observations of 4 variables. In fact, if we type it here, collapsed, you can see that's exactly what it is. So for subject 1, set size 1, not present, you have a mean RT of 454. All of those trials that met that condition are collapsed down into the mean of those RTs. Same thing, subject 1, set size 1, probe is present, 396. And we just keep doing that all the way through our 25 subjects, 6 set sizes, and 2 probe conditions. Okay. So that's exactly what we expected. But it's not a very useful presentation for us right now. And so what we really want to do is we want to take these means and we want to collapse them even further. Why? Well, here's why. Look at the picture on the Sternberg plot. We want the mean over all subjects of 1 symbol, probe present, or probe absent, probe present. And then the mean over all subjects of symbol size 2, present and absent probe, etc. Right? So we need to collapse all these subject means down into just simply condition means. So we're going to do a little bit further collapsing. And we're going to do one further thing that we haven't done this semester, so this is kind of new for us. We're actually going to convert this from being a data frame, like you see right here, which is actually not very useful for us. We're going to convert it into a matrix, and it'll be a really nice thing that we can then pull a plot from very easily. So here's how we do it. Let me just make a little comment. What we're going to do, we're going to construct a matrix of means by set size and probe condition. Okay, so we're going to collapse over all the subjects now. So I'm going to call this means matrix, and I'm going to get it by taking that collapsed data frame. I'm going to pipe that into another group by and summarize set, but I'm going to group by only the present variable, or sorry, the set size variable, and the present variable. And then I'm going to summarize the mean over all of this. So I'm going to say little m equals mean of the MRTs. Okay, because remember, in this data frame collapse, the means are all represented by the letters MRT. So I want to take the mean of those over all participants. Now, if I do that, that's just going to collapse this thing further. It's going to collapse it down into 6 times 2, 12 things. But I want those into a matrix form. So here's what I'm going to do. I'm going to do a little thing called spread first. And if you're interested in what this is doing, I would invite you to Google spread tidyverse, and it'll tell you about this. But for right now, just know that this works. So I'm going to say key equals present and value equals m. And then I'm going to export that all as a matrix. So the way I do that is I pipe the result into an as matrix command. Okay, so take a good close look at that code, type Control-Enter, and what you'll get is a pretty magical thing. You'll get a thing called means matrix, which if you look is just a matrix of means by set size and probe condition. So this is kind of nice, right? If you look at this matrix, all your set sizes are the first column, right? 1, 2, 3, 4, 5, 6. All your open dots, right? On the Sternberg plot where the probe is not present, all your open dots are right here. All your closed dots are right here. So that's really, really cool. So let's just do that. Here's what we're going to do. We're going to define 3 vectors that just essentially extract those very convenient pieces of information out of this matrix. And I'm going to give them convenient names. So let's see. This one I'm going to call set size. And that's just going to be means matrix. And I'm going to tell it that I just want the first column. And the way I do that is just a comma 1. And that'll just spit out the first column. So Control-Enter. If you look down here in your environment, you can verify that set size is indeed just 1, 2, 3, 4, 5, 6. So these are going to be the x values of my plot, right? Now I'm going to denote P as the probe present items. All right, so these are actually this one right here, right? This is the third column of this means matrix. So I'll say means matrix, comma, 3. Okay. And then similarly, NP will be those for which the probe is not present. And that will be, in this matrix, the second column. So I'll say means matrix 2. There we go. So it looks like that's everything we need. Except for one thing. I want to look again real quickly at the Sternberg paper. You can see just very barely here that so the open dots are the NPs for us, and the closed dots are the Ps. But then there's these little horizontal bars. And these are actually the means of those two numbers, right? So for each set size, if you just go halfway in between the open dot and the closed dot, Sternberg puts a little horizontal bar. You go to number 2, the little horizontal bar is right between those two dots. Again here, again here. So that's what we want to replicate. Basically, we want to take the mean of P and NP, okay? And the way we can do this is a very slick command in R. We're going to call this M, just for means. All right, this is just overall mean. What we're going to do is we're going to use an apply command. Apply will take a function like mean and apply it to all the rows in a matrix. If you think about conceptually what we're wanting to do, we're wanting to compute the mean of this number and this number in the first row. And then we want to compute the mean of this number and this number in the first row. So instead of doing all those one at a time or making some sort of loop to do it, we can just use this apply command. And we can say the following. We want to apply the mean function. So we're going to say means matrix, and then we're going to apply over the second and third column. All right. So we're going to say comma 2 colon 3 to tell it that we're applying this to both the second and third column. Now we're going to put in a number here, and this number 1, if you look at the help command for apply, this number 1 means that I want to apply this down the rows. If you wanted to do columns, you would put in a 2. But I'm going to put in a 1. And then what function do I want to apply? I want to apply mean. Now this will be helpful to us in just a little while when we want to start doing standard deviations too. And so if I apply that, just hit Control Enter, you can see that M is the mean of P and NP for each of the 6 items. Okay. Believe it or not, we now have done enough work. We can start to make a plot, and we can start to get something that begins to build up this Sternberg plot. Okay. So let's do it. Let's make a Sternberg plot. Okay, we're going to do it with a plot command. Plot. Now, there's going to be several options that we do to this, so let's build it up a little bit incrementally. First thing that we do with a plot command is we tell it what the x values are and what the corresponding y values are. The first thing that we're going to plot are those little horizontal lines. We're going to do that by plotting some plus signs at those means. So the x values will simply be represented by the set size. Remember, that's just 1, 2, 3, 4, 5, 6. And the y values are going to be those means. So we'll just say y equals capital M. Now, if we just did this right now, this would give you some dots at there, but that's not what we want. We want this to look a little bit better. So we're going to make a little bit better plot. So after the y equals M, I'm going to hit comma and then return to move it to the next line. And I'm going to put in some options. First option I'm going to put in is a PCH command. PCH will just change the symbol here. I'm going to change it to a plus sign, which is the symbol 3. If you Google R graphics PCH, you'll see pictures that will show you all the different symbols that you can use. This is number 3. I'm also going to make them a little bit bigger, and so that's a CEX command. I'm just going to say CEX equals 1.5, 1.5 times the normal size. And then I'm going to give it a good labeling. So I'm going to say xlab equals, and I'm going to use what Sternberg does, number of symbols in memory, something like that. And then my ylab, I'm going to use RT parenthesis in ms for milliseconds. And then the last thing I'm going to do is work on my my y-axis. I'm going to give it a little bit more vertical spacing. So I'm going to say ylim, and I'm going to go from, let's say, 650 up to a little bit more than what's up there. How about 950? Okay. So let's execute that entire code chunk. We'll do a control enter here on the first line. And you can see we've got a pretty nice little plot. I'm going to move this up here like that. Now, I know if you are thinking, if you're playing along at home, it doesn't look like Sternberg has pluses anywhere, right? But those pluses are going to get obscured by the error bars that we do in a little while. So essentially what's going to be left is the horizontal component of these. Okay, so first thing that you might notice is these aren't exactly a straight line, but they're pretty close. So the question might be, well, how close are they? Well, we can do that by fitting a linear model. So let's move this up just a little bit, and let's see how that works. So we're going to fit a linear model and very quickly add to the plot. So the way we do this is we define a model using the lm command, and then we're going to use another command called AB line to actually put the line onto the plot. So it's really easy syntax. We'll just say model equals, this is one of those things, you can name it whatever you want. I'm just going to call it model. It's the only model we're playing with today. I'm going to define it as lm, and then the notation is the y variable as a function of, which that's a tilde, that's above, it's right to the left of my 1 key. I do shift and then that little thing to the left of the 1 key. M tilde set size, right? This is the mean RTs as a function of set size. That's what that syntax means. So if I just hit Control Enter on that line, it defines a model for me. Now I can do a AB line command, AB line of the model, and that's actually going to add that line to my plot. There is the regression line. That's the line of best fit to those 6 means. So it's not bad at all. Now if you want to see the actual, the slope and intercept, so I mean you can tell right now the intercept is somewhere between 700 and 750, and it's kind of a little hard to tell what the slope is. But you can see exactly what those are by saying summary of model. In fact, that's good enough that we should blow this all up and look at it a little closely. So right here, you can actually see the estimates for the intercept and the slope. So this number that I've highlighted here, that is the estimate for the y-intercept. You can see it's right at 699. And of course, looking at the plot, that's a little bit... That's a little odd. Why is it there? That's a good question. So AB line's not exactly working quite right there. I'll have to come back to that. I may have been leaving something out here. That's very odd. But that's our estimate of the intercept. And then the slope is this number right here. That is the thing that's right beside set size. Now, what is all of this? Well, if you were to go and look at the Sternberg paper, you can see that he has something very similar here. He has this linear equation, which is an intercept. For him, it was 397.2 plus 37.9 times S, where S is the number of symbols in memory, or the set size. So that's his linear equation of this line that is fitting through the this line that is fitting through those means. Okay, so we have something very similar here. We have an intercept and a slope. And so that's kind of cool. Now we're going to talk a little bit more about this next week, but that's essentially what you're seeing right now. Okay. All right, so we've got the line up here. And again, I'm not entirely sure what the fit or why that intercept isn't exactly 700, so I might do an addendum to this to figure that out. But nonetheless, we will move on. We've got a nice fitting line here. And now the question is, well, how do we get those dots, right? The Sternberg had dots for the NPs and the Ps, and also the error bars. Well, we're almost there. First of all, the dots are really easy to add. So let me show you how to do those real quickly. So let's add dots for P and NP probe conditions. All right, so we do that with the points command, and we can just say that our X is set size, just like before, and we'll define Y to be the P condition, and we want those to be solid. So we're going, how are we going to do this? Is it PCH equals 1? Hang on one second. Nope, that's not what we want. We want PCH equals 19 on these. There we go. So 19 will give us the probe present condition. 19 gives us a solid dot. I'm not entirely sure why PCH equals 1 is open and you have to go all the way to 19 to get a solid dot. But it is, that is exactly what it is. So if we use PCH 19 there, then we get the right visualization. So these are the probe present conditions. Now we'll do the same thing for the NPs. So we'll say points, again, X is set size, but this time Y equals NP. And here we'll use PCH equals 1. All right, and so this gives us our open dots. And you'll see that the little pluses that we have are right in between the two pairs of dots. So that tells you that we're doing something right here. And if we go back and look at Sternberg, you see it's really kind of starting to look like what he gave us. Okay. All right. The last thing left to make before our Sternberg plot is finished is to get the error bars. So one might wonder, how do we get these error bars? It takes a little bit of reading, but if you read through the Sternberg paper, you can see that what he's doing is the standard error of those subject means. So remember before when we looked at collapsed, remember that data frame collapsed, those were all the subject means, okay? So what we want to do is we want to, let's see what we want to do. We've got those subject means. We want to turn those into a matrix, basically. And then we can find the standard error of that matrix somehow. So let's see how we can do that. I'm kind of coding this on the fly with you, so if I mess up, we'll just delete it and start over, okay? So the first thing that we're going to do is we are going to first build a matrix of subject means by set size, okay? So we'll call this subj means. Again, you can call it whatever you want. That's what I'm going to call it here. Subject means. We're going to start with that collapsed data set. We're going to pipe that to a group by and summarize command. So we're going to group by subject number and set size. And then we're going to summarize just like before. M equals mean of the MRTs. Then we're going to spread over subject number and the mean. So we'll say key equals subject number and then value equals M. And then we'll turn that into a matrix. Okay, so it's kind of the same sort of flow that we did up above, but it's a little bit different data frame. Let's see what this looks like. Okay, in fact, I'm going to blow this up just a little bit so you can see this a little easier. So if I type in subj means, you'll see what we have is we have a big old matrix where the rows are the 6 set size conditions and the columns are the subject numbers. Okay. And so this is kind of advantageous because it represents all 25 of our subject numbers in each row. So now we can actually compute the standard error across those means, right? So we'll take the standard deviation and then divide by the number, which is 25 in this case. So how do we do that? Well, it takes a little bit of doing in R, believe it or not. It's not quite as easy as you might like. So just walk with me carefully here and we'll show you how this works. First thing we need to do is realize there's no standard error function. You know, there's an SD function, right? That works just fine. It works, right? There's that standard deviation. But is there a standard error function? No, there's no SE. We have to actually build it ourselves, okay? Which is easy enough to do. Remember, standard error is standard deviation divided by the square root of the number of the data set, right? The size of the data set, so square root of n. So here's how we can do this. We can say SE equals function of x, and then how do you get this? Well, you take the standard deviation of x and you divide by the square root of whatever the length of x is. So this is a function now that I can apply to a vector and find the standard error. And the way it does it is it first finds the standard deviation and then takes the square root of its length. All right, so that's a way that you can make R do the standard error function for you. And now what we're going to do is we are going to take that subject means matrix, right, this thing right here, and we're going to compute the standard error of each row. And the standard errors are then going to be the height of our error bars for our plot. And we're going to do that. Remember, if you've got a matrix and you want to compute something over a row, you can use the apply command. So we're going to say that capital SE, just to differentiate it from lowercase se, which is a function, capital SE is, we're going to say apply, and we're going to go on subject means, and we want to use rows. Let's look at subject means again. We don't want to do anything with the first row. We want column. We don't want to do anything with the first column. We want to operate on the second column all the way to the 26th column. All right. Even though it's labeled 25, it's the column number is one later than that. So the way we're going to do this is we're going to say apply to subject means, but we only restrict to the columns 2 through 28, or sorry, not 28, 26. Okay. There we go. And again, we want to go by rows, so we put a 1 in to indicate that. And then what function do we want to apply? Well, before we did the mean, right? But that's not what we want to do this time. We want to do the standard error, which we have defined as this function called SE. So we'll just put SE right there. And now if we hit Control Enter on this, and just type SE, you'll see that these are the 1, 2, 3, 4, 5, 6 SE values. These are the 6 standard errors that we can then put on our plot. All right, so how do we do that? It's time to add the whiskers. All right, this is the last thing. Right, is it? Let's check. Yep, that's the last thing that we need on this plot. As I said in the assignment, we're not doing this little dash line right here, so we just need the whiskers. So how do we do that? Well, we're going to use something called the arrows command. You might think, well, these aren't arrows. Well, they're arrows if you flatten them, right? So that's what we're going to do. We're going to put in a couple of commands here, or a couple of options that will flatten these arrows for us. So the way the arrows command works is you give it a starting point and then an end point. So let's do this. We'll say x0. So this is like the initial point for the x's. That's just going to be set size. Okay. And then the initial values for the y's are going to be at the m's. Because what we're going to do is we're going to start at the mean and then go up by the standard error. Mean up by the standard error. Mean up by the standard error. So here's how we do that. We'll say x1 equals set size. But then y1 is going to be the mean plus the standard error. Okay. Let's go ahead and, well, no, let's not do anything. It's going to kind of mess things up. If you hit enter right now, you'll see why it's called an arrows command. It's a big old ugly arrow up there. I don't want that. I want to change something a little bit. So I'm going to do two things. I'm going to say length equals 0.05. Why? Because it works. All right, it's in inches, so you can try whatever you want there. But 0.05 looks nice. And then angle equals 90. Now you've got enough that you can do something. Let's hit Control Enter. And you can see we've got a nice little set of whiskers going up above the means. And see how now the little plus sign is sort of occluded? We can do the same thing, but now below. So actually, I'm just going to copy this entire command. But instead of doing mean plus SE, I'm going to say mean minus SE. That's going to put the whiskers now below. And now you have a Sternberg plot. You've got the regression line, you've got the means, you've got the open and closed dots, and you've got the whiskers, which is exactly what we wanted. So this is a great place to start. Now there's a lot more that we can do with this Sternberg plot. We're going to do that in our next class. But there's one last thing that I kind of wanted to walk you through. And that was, let me clear this out a little bit, Control L. I wanted to look at that model again. So I'm going to say summary of model. And one of the things that I wanted to point out, so this is the slope and the intercept and slope respectively. But there's also something called R squared. Okay? R squared is essentially a measurement of how much of the variance in the response times is taken up by this set size variable. As you can see, this is about 95%. You might think, well, is that good or bad? Well, if you look at the original Sternberg paper, and I think you have to find it up here on the third column of page 1, you'll see that in his model, he says linear regression accounts for 99.4% of the variance in the overall mean response latencies. So what we're getting in this kind of slipshod approach is not bad. We're getting around 95%. You might be wondering, where does that 95% come from? Well, I'm going to show you real quick. If we say ANOVA of model, this will actually give you the ANOVA table for the linear regression model. And if you pay attention to this sum of squares column, sum of squares is essentially a measure of variance, right? If I were to take the sum of squares that's due to set size, that's 12,748.7, and divide by the total sum of squares, so what I get by taking 12,748.7 plus the residual or errors, okay, you'll notice that as a fraction I get 0.9508, or sorry, 0.9509, which is exactly what r squared is here. So that's where r squared comes from. It is a measure of the total variance in the model that's explained by our predictor of set size. So it basically says that there's only about 5% that's left over for unexplained variance. So that's really, really good. So this plot we're seeing kind of indicates that for us, that this plot fits those mean response times very well. So this is how you do it, guys. This is how you get your Sternberg plot. The next step, of course, is going to be trying to interpret what all of this means. But for now, let's take it a step at a time, and let's work through the data, and let's get a plot. Remember, with your data, your numbers might be slightly different because you may have a different data set, and you certainly will probably have a different number of subjects. So make sure you pay attention to what the code is doing, and so that you can adapt it accordingly. So that's all for this video. It's a lot, but you're going to get something really cool out of it, and it'll give us some cool things to talk about and figure out a little bit about the architecture of processing things in short-term memory. So that's all for now. We'll see you next time.